As we continue our work with trig ideas, we're going to go back and do some review about radicals. We're going to review the Pythagorean theorem, and then we're going to talk about special right triangles in this section. So the first parts of this is just reviewing that radical operations and simplifying that we did at the beginning of the quarter in our expressions unit. And so remember, when we are simplifying radicals, we're really looking for perfect squares because squaring and square rooting are opposite operations. And so we just begin factoring. I know that 2 goes into 112 56 times. I know that 2 goes into that another 28 times. And then I know that there's a 4 and 7. Now when I get to the end of my factor tree, I just go ahead and I think about, well, 2 and 2, that's 2 squared. That's a perfect square. Square root of 4 is 2, and then that leaves a leftover 7. And so 112 reduces to 4 square roots of 7. And we remember, when we bring numbers out, they get multiplied. So 45 is 9 times 5. 9 is a perfect square. Square root of 9 is 3. That left of 5, so I have 15 square roots of 5. Remember, we can never leave a radical in the denominator, but this is one of those scenarios when both numerator and denominator are under the radical. So I can go ahead and simplify first. I know that 24 and 80 both have a common factor of 8. So when I take that out, that leaves 3 over 10. Now, 10 can't be left in the denominator, so I need to multiply top and bottom by the square root of 10. Square root of 3 times the square root of 10 is the square root of 30. The square root of 10 times the square root of 10 is the square root of 100. That's going to simplify because I made it so square root of 100 is 10. Remember, that denominator doesn't disappear. We're not canceling when we rationalize. We're just putting it into proper math form. We can't have that radical in the denominator. And since the square root of 30 is under the radical and 10 is outside, we cannot cancel in between. There are no perfect squares in 30, so we are done. Example D, the 2 and the 24 can't cancel because the 2 is outside of the radical and the 24 is under. But the square root of 3 and the square root of 24 can cancel, and that would leave me the square root of 8 over 2. But 8 is not in lowest terms because 8 has a 4 in it. So the square root of 4 is 2 square roots of 2 over 2. This is all multiplication, so those cancel. So my reduced simplified answer is the square root of 2. This should all seem very familiar because we covered this in the first algebra expressions unit. Remember, when we multiply two radicals, we can just go ahead and put them together. But I'm not going to multiply 6 times 18 and then factor. So I'm going to think about this as 6 times 6 times 3, and that 6 times 3 is 18. Well, then it's clear to see there's my perfect square, which comes out, and that simplifies to 6 square roots of 3. Remember, variables, we think about them in groups of squares. K squared times k is still k cubed. That k squared will come out, and I will have k square roots of k. In the same way here, the square root of 27 and the square root of 48 will cancel, and those have a common factor of 3. And so if I take that out, and if I think about it like this, I kind of just separate the radicals out, the square roots of 3 cancel, and I'm left with perfect squares. So I have 4 times 3 over 4, and then those 4 canceled, and 3 is your answer. So just some quick specific work on rationalizing the denominator. This is bad math grammar. You can't ever leave that radical in the denominator. So what I want to do is I want to go in, just like making a common denominator, I want to multiply top and bottom by the value, square root of 2 over the square root of 2. That is really 1. So I'm not changing the value. So what happens is I have the square root of 2 over the square root of 4. The square root of 4 can be simplified, so I have the square root of 2 over 2. Here I would multiply top and bottom by the square root of 3. And so I'd have 5 square roots of 3. The square root of 3 times the square root of 3 is the square root of 9. Square root of 9 is 3. So that squaring and square rooting undo each other. Here I've got to multiply by the square root of 5 top and bottom. These two get multiplied, so I have 3 square roots of 10 over 5. There's no perfect squares in the square root of 10. I can't cancel the 5 and the radical 10, so that is my answer. In this one, the square root of 3 and the square root of 6, those are both under the radicals, and so I can cancel. And so I'm left with 2 square roots of 2 over 3, and that is in lowest terms. Now that all is going to come into handy when we talk about our special right triangles. Now also as review, we're going to talk about the Pythagorean theorem. And the biggest thing with the Pythagorean theorem is to find your right angle and find the side opposite, because that is the hypotenuse. And that is always where you start. C squared is equal to A squared plus B squared. The A and the B don't matter. Those are just the legs. The C squared is always the hypotenuse. The hypotenuse is always the longest side. So if you find that right angle, go across from it, that will be your hypotenuse, and that's where you should start. Then you solve for what you don't know. So a couple of really quick, and notice we're going to go exact, so we're going to take square roots and we're going to simplify. The very first thing I do is that, so I know I'm going to start here. 10 squared is equal to 6 squared plus b squared. And so I have 100 is equal to 36 plus b squared. Subtract 36. 64 equals b squared. I'm going to take the square root of both sides. Because this is a length, I do not have to consider the negative, and so b is 8. Here, lowercase b is the side I'm missing. That is the hypotenuse, so I have b squared is equal to 5 squared plus 12 squared. I have b squared is equal to 25 plus 144. B squared is equal to 169. Go ahead and take the square root of both sides. B is 13. That works great because it is bigger than all of the sides. And that's what we need to have happen for our hypotenuse. Now the problems can get a little more complicated looking. But if you remember, these hash marks mean this is an isosceles triangle. When we have that perpendicular segment and those pieces equal, that means these pieces down here are equal. So that means that is 4, since the whole thing is 8. This is a leg that I don't know. So clearly here's my right angle. Here's my hypotenuse. So I have 5 squared is equal to 4 squared plus a squared. And 25 is equal to 16 plus a squared. A squared is 9. A is 3. Even when we're tipped sideways, just find that right angle. 12 squared is equal to x squared plus 8 squared. And when you work that out, we end up with x is the square root of 80. Now we have to do some work to see if there are perfect squares there. Well, I know that 4 is going to go in there times 20. And I know 4 is going to go in there again times 5. And so my 2 4s will come out. That'll leave 5 underneath. And so x is 4 square roots of 5. And that is the exact answer that we want to be working with. Now this is going to combine our factoring that we just got done working with our Pythagorean theorem. Now remember, any expression is a single number. Here's my right angle, here's my hypotenuse. So x squared is equal to x minus 2, the quantity squared, plus 4 squared. Now remember, x minus 2, the quantity squared, is really x minus 2 times x minus 2. So we have to FOIL that out. First two terms, outside terms, inside terms, last term. So I have x squared is equal to x squared minus 2x plus 4 plus 16. So I've got x squared is equal to x squared minus 4x plus 20. Now, when I have x squared and x, flowchart says set it equal to 0. But when I go to subtract x squared from both sides, I can see that x squared minus x squared is going to cancel. So now really, I just have an x item. So the flowchart says separate your constants from your variables. So I have negative 20 is equal to negative 4x. Divide both sides by negative 4. X is 5 and is a positive value like we would expect. So we can also look at some word problems, and I'm going to save those for the next video.